Testing, can you hear me? Okay, I'm public now. Hope you guys can hear me. So I'm going to be studying discrete math again. And last stream I studied exponential sequences. This stream I'm going to start the next chapter. It's called proof by induction. What is the unit digit of 6 to the power of n? Does your answer depend on n? Hold on. Unit digit. So 6 to the power of minus 6. 6 to is 36. 6 to the power of 3. 216. 6 to the power of n is equal to 6 times 6 to the power of n minus 1. Oh, wait a minute. When we are multiplying a number, say this is the first digit, second digit, third digit, fourth digit, and so on, and then the last digit is 6. last digit is 6. If we multiply this number by 6, we get 36 over here, right? And then 3 carry. And this will happen with any number. So yeah, it will always, the unit digit will always be 6. Mathematical induction is a powerful proof technique that can be used to prove statements are true for a sequence of statements, as long as that sequence of statements has some starting place. For example, if we are trying to say something about the unit digit of 6 to the power of n, we are making that claim for n is equal to 1, n is equal to 2, and then n is equal to 3, and so on. Induction is closely related to recursive definitions. The main idea in a proof by induction is to explain how you can get from one statement in the sequence to the next. Suppose we have this. Suppose that this had a 2 for its unit digit. What the unit digit of 6 to the power of 473 be? So we multiply this by 6. 6 times 2 is 12. So we get 12, right? Wait, how do I? Okay. There's no option to input. Unit digit of 6 to the power of 2, 6 to the power of 3, 6 to the power of 4. It's all 6. Unit digit is a 2. The unit digit of k plus 1 is a 2. Okay. 6, then this is true. This is true. We have seen that describing a sequence recursively can often be easier than describing the sequence with closed formula. We will now see how using similar recursive reasoning can help us prove statements using a proof technique called mathematical induction. This style of proof is especially useful when the different instances of the statement are related recursively. For example, suppose we want to prove a fact about all the terms in a sequence for which we have a recursive definition. Consider the sequence n more than or equal to 0 defined recursively by n is equal to 3 times an minus 1 minus 2 with a0 a being equal to 5. How could we prove that every term in this sequence is odd? Let's write by starting out the first few terms of the sequence. 5, 13, 37, 109. They're defining it recursively, right? They're saying n 3 n minus 1 minus 2. Like that. And the sequence is 5, 13, 37, 109. So 3 some odd number minus 2 will give us 6a plus 3 minus 2, which is 6k plus 1, which is odd because I can write it as 2q plus 1. Can write it as 2 3k plus 1, and this number is odd. Induction can prove many statements that hold for all natural numbers. not just statements about sequences. In particular, induction should be used when there is some way to go from one case to the next. And you can see how to always do one more. Thinking about how we write statements in logical symbols, we will use induction to prove statements of the form for all n Pn where the domain of the discourse has some least element. Say that domain of discourse is the natural numbers. We are then proving this sequence of statements P0, P1, P2, P3. The way we do this with induction is to prove a base case that P0 is true where P or PA where A is the least element for our domain of discourse. Next, we prove the induction case that Pk is equal to Pk plus 1. Oh, that Pk being true implies Pk plus 1 is also true. Together, these are enough to prove Pn is true for all n. That is, why is this style of proof valid? Well, let's convince ourselves that P3 is true. We know P0 is true. Because we know P0 is true, then P1 is true. Then also know that P1 is true. Because P1 being true implies P2 is true. We then get that P2 is true. Finally, because P true implies P3 is true, we have that P3 is true. Induction proof structure. All right. Base case, prove that P0. Inductive case, Pk implies Pk plus 1. So you can assume Pk is true. Pk is called the inductive hypothesis. You must then explain why Pk plus 1 is also true given that assumption. Prove that for all n, 6 to the power of n minus 1 is a multiple of 5. I mean, all numbers in a form of 6 to the power of n. All numbers, yeah, all 6 to the power of n numbers, they end with a 6, right? So if we subtract 1, they will end with a 5. And any number that ends with a 5 is a multiple of 5. But we have to use induction to prove this. Uh, the above two example, we started with n is equal to 1 or n is equal to 0. You can start later if we need to. If this for all integers more than 5. With great power comes great responsibility. Induction isn't magic. It seems very powerful to be able to assume Pk is true. After all, we are trying to prove Pn is true, and the only difference is in the variables k versus n. Are we assuming that what we want to prove is true? Not really. We assume Pk is true only for the sake of proving Pk plus 1 is true. Still, you might start to believe that you can prove anything with induction. Consider this incorrect proof that every Canadian has the same eye color. Let Pn be the statement that any n Canadians have the same eye color. P1 is true since everyone has the same eye color as themselves. Now assume Pk is true. That is, assume that any group of k Canadians that in any group of k Canadians, everyone has the same eye color. Now consider an arbitrary group k plus 1 Canadians. The first k of these must all have the same eye color since Pk is true. Also, the last k of these must have the same eye color since Pk is true. So, in fact, everyone in the group must have the same eye color, thus Pk plus 1 is true. Really, something went wrong. The problem is that the proof Pk implies Pk plus 1 assumes that k is more than or equal to 2. We have only shown P1 is true. In fact, P2 is false. Okay. Okay, this example I didn't clearly understand. Suppose you wanted to prove using mathematical induction that 135 135 to n minus 1 is equal to n square for all values of n more than or equal to 1. Which of the following would be an appropriate first line of the proof? Okay, this is true. The sum of the first n number. I think it's only this, right? We have one answer and got zero correct or two needed. It's this. Sum of the first n odd numbers in n square. Okay. Okay, then we have to define p first. Suppose you're trying to prove by mathematical induction that the statement Pn is true for all n more than 0. What would you attempt to prove in the induction step of the proof? That Pk implies Pk plus 1 for all k more than or equal to 0. Okay. Suppose you wanted to prove the following statement. What would be the first line of proof by induction? So we define Pn, right? Let Pn be the statement. Yeah, like that. Suppose you were proving the following statement by mathematical induction. What would you need to show to establish the base case? Show that P1 and P2 are both true. Show that P1 implies P2. Think it's this? Yeah. Show that P1 is true. What would be the first line of the inductive case? Think this. Assume Pk is true. No, for all k more than or equal to 1, that is, assume this is equal to this. Assume Pk is true for some arbitrary k more than or equal to 1. So we have to prove this for all k more than or equal to 0. Arrange some of the statements below to create a correct proof by induction that the recurrence relation this with the initial condition a00 has the closed formula an is equal to 5 n minus 1. So we define the Pn statement first. Assume that Pk is true. Then we assume this. Assume Pk is an 5 n 5 to the power of n minus 1. We note this 0. So P0 is true. Then we do this by the recurrence relation we have. I think this is it. Assume PK. Think this doesn't get included, right? Then Kn plus 1. Oh, wait, this. Then AK is equal to 5 to the power of K minus 1. And then we note this, right? I don't know why this is wrong. This simplifies to this. So PK plus 1 is true. What is the answer? I don't get what's wrong. We may have answers for this additional exercise. Additional. Nope, we don't. Okay, let's do additional exercises. Number 3. Actually, let's do number 2 first. Additional exercises number 2. Use induction to prove for all n, which is a element of natural numbers, that 2k 2n plus 1 k is equal to 0. So 2 is equal to 0 is 1. 2 is equal to is also 1. Pk is the entire statement, right? P is a proposition. P0 is true. 2 to the power of 1, 2 to the power of n plus 1. It has to be the sum. 2 to the power of 0 and 1, right? Zero. Two to the power of 0, 2 to the power of 1. So 2 to the power of 0, 2 to the power of 1 is 2 to the power of, yeah, 1 plus 2, which is 3. 4 minus 1, 3. P1, true. 1, 2, 4. 4 to 1 is 7. And then 2 to the power of 3 is 8 minus 1, 7. Now what we have to prove, it works for some Pn. Now we have to prove for Pn plus 1. This is equal to 2 to the power of n plus 2 negative 1. Uh, how do we write like a statement is this thing? What's the notation? Is it like this? So Pn is this. Or is it just equals to? No, that doesn't make sense. Equals to is used here. Sum of k plus 1. So from this side, we have k is equal to 0 to the power of n plus it with 2 to the power of n plus 1. This is equal to 2 to the power of n plus 1 plus 1 minus 1. Actually, no, this is wrong. This is wrong. I have a better idea. So sum of the am I doing this correct? Um, so Pn is this. Pn plus 1 is this, right? Hold on, let me think about this. Okay, I have no clue. Hold on, I think I have an idea. We can use combinatorics here. So like, can choose one, can choose two. Then we plus it, right? Yeah, this is the binomial theorem basically. Maybe we can use this. Let me think. Okay, I have an idea. K plus 2k is equal to 0, 0 plus it with. I don't know if this is like the right answer. Uh, it's the sum of all this. Because 2 to the power of 0 is this, 2 to the power of 1 is this, 2 to the power of 2 is this, right? Or wait, power of 0, power of 1, power of 2. Yes, yes. Um, so now we take all this. We do plus 1 here. Then we will be left with this. This is they're saying this is 2 to the power of n plus 1 minus 2 to the power of n plus 1 minus 1. I want to see the answer. Use induction to prove this. Okay, I think I have an answer. Let's assume Pn plus 1 is true. So we have we have this, right? This is plus 1. So this is 2. And on the left hand side, we have 2 to the power of k from n plus it with 2 to the power of n minus 1. N plus 1, yeah. Then that proves it. Oh, this was much simpler than I thought. I don't know why I always use combination. There we have it. So we just reverse this reasoning and then we get our proof. Okay, next chapter. Start with a square piece of paper. You want to cut the square into smaller squares, leaving no waste. Obviously, it is impossible to cut the square into 4 squares. You can also cut it into 9 squares. Turns out you can cut the square into 7 squares, although not all the same size. What other number of squares could you end up with? Square, you want to cut this into smaller squares, leaving no waste. Cut this into 4, and cut this into 9. How do we cut this into 7? Square. Um, yeah, how do we cut this into 7? Turns out you can cut the square into 7 squares. 7 is an odd number, like, although not all the same size. Sometimes to prove pk plus 1 is true, it will be helpful to know that pk and pk minus 1 and pk minus 2 are all true. This is certainly the case when proving something about a recurrence relation that is given as a combination of two previous terms. Prove that 2 to the power of n is a solution to the recurrence relation. Uh, okay. Mm, so A0 is 1 and then A1 is 2. So A3 is 5 times 2, 6. Right into which is 2 to the power of 2. Sorry, this is A2. 5. You have n minus 1, so we have 4 minus 6 times 2. 5 times 4 is 20, 6 times 2 is 12. So we are left with 8. It's 2 over 3. If this is true, so this part we know for certain is true, right? Now, how do we would prove for n plus 1? We multiply by both sides. Then we have n plus 1 minus 6 n minus 1. Therefore, and that proves it, right? Solution. Yep. Consider the following puzzle. You have a rectangular chocolate bar made up of n identical squares of chocolate. You can take such a bar and break it in along any row or column. How many times will you have to break the bar to reduce it to n single chocolate squares? At first, this question might seem impossible. Perhaps we meant to ask the smallest number of breaks needed. Let's investigate. Suppose you start with a 1 by 3 bar. How many breaks would you need to reduce it to a single square? 3. 1 by 3 bar. You mean 1? You can get a single. Hold on. Oh, I need only 2 breaks, right? To get 3 squares. If you had a 1 by 4 bar, how many breaks are required? 3. First, guys, arrange in 2 by 2 square. First break would require you to break the chocolate into 1 by 2 bars. Then you would require one more, actually 2 more breaks for a total of 4, for a total of 3. Wait, what? 2 by 2 squares. One break here, then each of these would require one break. A 6 square bar could either be 1 times 6 requiring 5 breaks or 2 by 3 bar. There are two ways to proceed now. Break the bar into 1 by 3 bars, each requiring 2 more breaks for a total of 2 plus 2 plus 1, 5. Break the bar into 1 by 2 bar and a 2 by 2 bar. 1 by 2 bar takes one more break. 2 by 2 bar takes 3 more breaks for a total of 4. 1 by 2 bar takes one more break and the 2 by 2 bar breaks takes 3 breaks. Three plus one, right? What's the issue? Break the bar into 1 by 2. 3 plus 1 plus 2, right? 6. Wait. So a break here. Uh, um, hi- okay, a break here, right? Yes. So one break and then two, one, one, two, three, four, five breaks. But we can break it into 1 by 2 bars. So one break, two break, then one, two, three, five, right? They say 2 by 3. Break the bar into 1 by 2 and 2 by 2. Yes, yes, five. Based on the above data, what should a conjecture be for the number of breaks to reduce an n square bar to a single square in terms of n? It will take these many breaks to reduce an n square bar to a single square. So for 6, we have let's say 1 by 3 bar. How many breaks would you reduce it to? 1 by 4 bar. How many breaks are required? 3. But if the four squares are arranged in 2 by 2, then the total is also 3, right? One, two, one, two, three. But if it's 6 square bar, requires 5 breaks. 2 ways to proceed. This will require 5 breaks as well. So what about this? N, I guess n minus 1 breaks. Do we believe this? Suppose you used one break to reduce the bar into two smaller bars, A and B squares respectively. The conjecture is correct. How many more breaks will it take to reduce the size A bar? Uh, Suppose you used one break to reduce the bar into two smaller bars. Conjecture is correct. How many more breaks will it take to reduce the size A bar? A minus 1. Size B bar. B minus 1. How many breaks will this take altogether? A minus 1 plus B minus 1 and then plus 1. What is A plus B? We got A and B by breaking n squares into two pieces. So A plus B is n, giving us the total number of breaks as n. Oh, n minus 1. Think of recursive definitions as instructions for building a ladder. You can build the ladder as tall as you like because you have instructions for building the next rung, as long as you are standing on the rung before it. Induction is the corresponding proof technique to prove that you can climb the ladder as high as you like. You prove that you can step onto the ladder, then prove that from any rung you can get to the next rung. More specifically, suppose you were trying to prove that you can get to rank 4 on the ladder, you have successfully proved that you can get to rank 1 and that from any rank you can go to the next. You can get to rank 1 and from rank 1 you can get to 2. From 2 you can get to 3. Therefore you can get to 4. But notice that along the way you know you have visited ranks 1 through 3. We might as well assume that we have visited all the ranks below the next one we are trying to reach. This is the idea behind strong induction. A better ladder metaphor for strong induction is to think of ladders as things we can stack on top of each other. You want to argue that it is possible to climb 20 rungs of ladder? Let's divide it into two smaller ladders. See a 12 rung ladder and an 8 rung ladder. You can assume that we can climb both of these since 20 is the least size we are not yet convinced of. Well, put those two ladders together and you get 12 plus 8 is equal to 20. Start by saying we want to prove let P n be a statement, then establish two facts: base case, inductive case. So assume Pj is true for all j less than or equal to k, prove that Pk plus 1 is true. Of course, it is acceptable to replace 0 with a larger base case if needed. To illustrate strong induction, let's return to the chocolate bar problem. Given n square rectangle chocolate bar, it always takes n minus 1 breaks to reduce the bar into a single square. Let Pn be the statement it takes n minus 1 breaks to reduce n square chocolate bar into a single square. Fix an arbitrary k is more than or equal to 2 and assume Pj is true for all j less than or equal to k. Consider a k plus 1 square rectangle chocolate bar. Break the bar once along any row or column. This results in two chocolate bars, say of sizes A and B. That is, we have A square rectangular chocolate bar and B square rectangular chocolate bar. And AB plus is equal to k plus 1. We also know that A is less than or equal to k and B is less than or equal to k. So by our inductive hypothesis, PA and PB are true. To reduce the A square bar to single squares, take A minus 1 breaks. To reduce the B square bar to single square, takes B minus 1 breaks. So we already did that in the exercise. Prove that any natural number greater than 1 is either a prime or can be written as a product of primes. Hold on, that isn't that trivial? If it's not prime, no, it's not trivial actually. Wait. That's the fundamental theorem of arithmetic, right? Uh, Greater than 2, right? Greater than, yeah. We have 2, actually. 2, 3, 4, which is 2 times 2, 5, 6, 7, 8. I should write 2 square here. 5 times 2, and then 11, 12, 13, 14. Okay, so we have the base cases. And now let k be equal to p to the power of a1, p to the p1, p2, p3, and then p pn to the power of a n. We know that this exists, right? But then but then the fundamental theorem of arithmetic says that we can uniquely represent it as a product of prime. There's one unique representation, right? I can't remember it clearly. N is either prime or can be written as a product of primes. Base case is true. You want to show pk plus 1 is true. Either prime or a product of prime. If k plus 1 is a prime, we are done. If it is not, if then k plus 1 has more than two divisors. You can write m1 plus m1 times m2 with m1 and m2 less than k plus 1. Oh, and then each m1 and m2 they have a prime divisor. By inductive hypothesis, m1 and m2 are either primes or can be written as a product of primes. In the case, we have that m1 times m2 is equal to k plus 1 can be written as a product of primes. Thus, by strong induction, Pn is true for all n greater than 2. Hold on. But there is another thing. Fundamental theorem of arithmetic. Yeah. It is possible that n, oh, I switched n and k. P1, P2, P3, Pk. Or what this is trying to prove is that it can uniquely be represented, right? We first show the existence of these products and then we will prove the uniqueness. Given an integer n greater than 1, n is prime or composite. If n is composite, then there should exist a prime that divides it. The resulting number would either be a prime or composite. We keep repeating this process, we will end up with n is equal to p1, p2, p3 all the way till pk, where pi is a prime and where some primes may occur multiple times. This shows that some product of for n exists. Okay, I need to revise this proof in particular. In its composite number, then there is a prime divisor less than or equal to root n. Because there is circular reasoning over here. It could be possible that n is equal to p1, p2, p3 all the way till pk is equal to p1, q1 is equal to q2, q3 all the way till qh. H is greater than or equal to k, where qi is either prime or 1. If n is equal to p1 all the way till pk, which is equal to q1 all the way till qh, this is proving uniqueness. Then we rearrange this. Since P2, P3 all the way till Pk is an integer, then P1 divides this, right? Okay, this is an integer, then that means this division gives an integer, right? So P1 divides all of this. So either, okay, so either P1 divides Q1 or P1 divides Q2 or P3. P1 divides Q3 or so on. If, yeah, if this, then this, okay, I think I wrote the same thing. By repeating this process, we can claim that one of these has to be true. P1 divides Q1. Oh, I see what I'm doing here. According to this lemma, either P1 divides Q1 or P1 divides Q2, Q3 all the way till QH. If P1 divides Q3, Q2, Q3 all the way till QH, then either P1 divides Q2 or P1 divides from 3 all the way till H. By repeating this process, we can claim that one of these has to be true. P1 divides Q1, P1 divides Q2, P1 divides Q3. Let's assume Q1 is the prime that can be divided by P1. Since Q1 is a prime, then P1 is equal to Q1. So now we have this, and now we put P2 to the other side. Now P2, since this is an integer, P2 divides this thing, right? And assume it's Q2 that gets divided by P2. And then we are left with this, and then we repeat the process with P3. Then eventually we will end up with this. This means only k numbers of Qi integers were primes. Only k numbers of Q1 integer were primes. And all those Qi primes were equal to some Pj primes. This proves the uniqueness. I need to reword some of this. Whether you use regular induction or strong induction depends on the statement you want to prove. If you want to be safe, you could always use strong induction. It really is stronger, so you can accomplish everything weak induction can. That said, using regular induction is often easier. There is only one place you can use induction hypothesis. There is also something to be said for elegance and proof. True. You can still prove the next case. You just get to assume all the previous cases. Okay, okay. Assume Pk plus 1 is true. Then prove Pj is true for all j less than or equal to k. You just get to assume all previous cases is true. Yeah, that's what they said here, no? Pj is true for all j less than or equal to k. Oh no, wait. You assume Pj is true for all j is equal to less than or equal to k, and then you prove Pk plus 1, right? Prove that P0 is true. Inductive case, assume Pj is true for all j less than or equal to k. Prove that Pk plus 1 is true. Let's say the following claims can be said about the relationship between proof by induction and proof by strong induction. Are true. Um, any proof by induction, any proof by strong induction can be written. Maybe this. You have one answer and got zero. Think this. You gave one answer and got one stronger because the base case is stronger. Okay, I will end the stream here then. I need to rework on my website. And yeah, I will see you guys next time then. Bye.